eliminate these common skulls.
Does anyone want to play PUBG with me?
Hey everyone, spam F. When we get into the plane, everyone spam F. Does anyone have a vertical folder?
Hello everybody and welcome to class today. Today we're going to be looking at managing storage for a virtual machine. We've got our stream objectives here for today. We are looking at understanding how virtual machines connect to storage resources. We're also going to talk about examining the configuration options for disk storage connecting to virtual machines. And we're going to examine different practices for tuning storage devices connected to virtual machines. So as we get into this, essentially we're talking about data storage. So data storage in today's world, I mean, we're basically looking at something that's ubiquitous, right? It's everywhere. So, you know, we see it all over the place. You know, it's in our computers, it's in our smartphones, it's even in less obvious places. You know, when we think about it in like a DVR, you know, we're storing hours of television content to our DVR. And now we're even moving toward cloud-based DVRs. And oftentimes, you know, we'll see these cloud-based DVRs being virtualized on, server, virtual machines built in server services. So, you know, having somewhere to store information, we need to perform our routine tasks are, one of the most important things. And, in virtualization, we're abstracting the storage resources. In order to do that abstraction of storage resources, it requires some good planning. But, there are many choices and many different strategies that we can use to virtualize storage, where we can make good use of the storage that we have. And there are many different technologies that we can utilize to kind of leverage as we build our virtual machines. So those are the kind of things that we're going to be looking at today. So the first thing I want to talk about is the connecting of virtual disks. So insofar as, oh, hi, Jorge. How are you doing today? Good to see you. The connecting of virtual disks. The amount of data being managed is rapidly growing, and we know that from that ubiquity of the need for data storage. Data storage is an ever-expanding resource. You only need to look at how much data you're having to store yourself to have an understanding of how necessary and how pervasive and how massive the amount of data storage need is becoming. We're now even seeing refrigerators that, need data storage. So this, data storage, insofar as all that goes, is becoming a huge business. So when we think about... So you got a question? Do you think that major companies are using virtual storage to segment user data, for example, for Google Drive? I would say yes. I would say probably so. That's what we're seeing. With a lot of AWS servers, unless you buy a dedicated server or virtualized servers, and if you get a Google distributed server, it's oftentimes a virtualized server. I would think there would be more, we would have more purposes there as to why we would virtualize the data and why we would virtualize the storage, rather, besides just segmenting it, making good use of our hardware and the things that we've talked about before. But I would say that, yeah, the devices that a lot of this data storage is on are probably virtualized devices, and it would do well to help segment user data. And I believe we might actually discuss that just a little bit here. Let me check my notes. Because really what we're, as the next bullet point here on our screen states, storage connects to virtual machines similarly to physical servers, but it's abstracted from the virtual machines. So, we've talked before about the way that hypervisors kind of manage the different pieces of hardware that are, on the host machine in comparison to the virtual machine. From a computer standpoint, whatever the computing device is, the process to obtain stored information to work on is, very similar. Right? The operating system, which is something that we've talked about before, kind of controls the access to various I/O devices, and then an application is loaded into memory, and based on various functions that it has to perform, it makes a request. And then the operating system gets the information to process. And, the operating system then kind of passes the information through and starts the whole starts everything on that whole process of the data cycle on the back end. So you have data moving through the RAM and into the processor and back out of the processor and so on and so forth. And, you know, the operating system's what transfers those data blocks to the program. And we see the same, but we see the same kind of things in the virtualized environment. You know, it works the same way. We just have the hypervisor on the other end. That's, you know, doing its hypervisor conductor business. You know, we've talked about, you know, I've kind of made the illustration of the hypervisor as the orchestra conductor before, where it's you know, it's conducting the band, basically, and making sure all of the hardware plays nicely with one another as it progresses and works with the virtual machine. So it's essentially working the same way on a virtual machine as it does on a physical host. It just has that additional element of the hypervisor in there doing its job. And a lot of the storage best practices that we utilize in a physical environment, like thin provisioning, which I think we'll talk about thin provisioning a little more in just a moment. But we can go ahead and define thin provisioning. Thin provisioning essentially being you know, kind of what we've done before. With creating hard drives where we're dynamically allowing those hard drives to grow. You know, if you thin provision disks, if you thin provision a disk at 100 gigabytes and it uses only 50 gigabytes, then you only have a 50 gigabyte disk space that's been allocated at that time. You know, it grows into that 100 gigabyte space later on. So, you know, it was the thing we were doing with VirtualBox VMs and Workstation Pro VMs, but it didn't necessarily call it thin provisioning. And we also have data deduplication, which is one of the things, you know, we kind of mentioned last week when we were talking about data blocking and things of that nature, where, you know, if we have a data file on different VMs that the different VMs are using, then instead of copying that data file across the VMs, it will use that one data file for the 3 virtual machines. And various other elements of that nature. And then just like the real world, you know, just like with physical hardware, you know, when you have your nice gaming setup, right? Your storage I/O is key for good performance. So you want those nice read-write speeds. That input-output from the storage medium to be able to get good performance out of your virtual machine. You know, it's so really, I mean, what we're getting to here is essentially just the fact that a virtual disk is, you know, even though it's different from a physical disk in terms of what it is, you know, it's abstracted. It's just a slice of a physical disk. And it could be, you know, different blocks from a single physical disk. the performance of that virtual disk, thanks to the hypervisor, is identical. And that's one of our goals of a virtual machine that we've talked about over and over and over again throughout the course so far. So what we have here is an example of how data storage actually works in a virtual environment. And this in particular is the VMware architecture that you see here. So we have our chart here. So in our little chart that we have here, essentially what we're looking at is the path that a request for data makes from the application program to the storage controller. So the request goes to the operating system, which determines the I/O device to which the request needs to go. Then direct attached storage, which is disk storage that is internal to the host system, being managed by the storage controller, which is a physical processor card that is part of the computer's hardware. And then we're also looking at, what would we have if we were working with a SAN or a NAS connected through the computer interface through the through physical I/O cards. On the network emulation side and on the storage emulation side. Or rather, let me take a little step back here. I've kind of got my notes jumbled up in a circle here. I could probably just kind of walk you through this in a little bit of a simpler way than the way I've tried to write my notes here. Let me grab my pointer. So essentially, we're looking here on our on this side of our diagram, and we're following the path down. The application makes a request to the operating system, and through the SCSI driver in the operating system, it's passing information through to the hypervisor. So then the hypervisor takes over as kind of with that conductor role to talk to the physical host. So it's picking up that storage emulation side there. It's looking at that virtualized storage, and it's saying, okay, let me pass this information through. Get into the storage driver, send that information through to the storage controller, and pass it on to the physical disk. And in turn, we're comparing that to kind of how network emulation works. Which is kind of how I got wrapped up in a circle here. The applications send a need for, something on the network through the NIC driver. It sends it through the hypervisor to do its job. That sends it on out to the physical NIC, which sends it on out to the physical interface. So we're looking at a very similar means of control between the storage medium here and the network medium. And it really makes sense when you think about it in terms of how the hypervisor handles things. Because, I mean, what is a hard drive, and what are you doing with a hard drive, but the fact that you're handling input and output requests. You know, so just like you're working with a network and you're giving input and output there, you know, you're uploading and you're downloading with your storage medium, you're sending input and output back and forth via this system here. So it kind of makes sense that the hypervisor would kind of handle the network card and the storage controller in a similar way. Our Zen architecture is very similar. And you can see how it's similar here. The only difference being that in this case, instead of the way it was on the other screen, we're passing through data blocks through a unique privileged guest that handles I/O rather than the hypervisor layer. So we have this DOM 0 layer here. That was a nice circling. Let me try that again. We have this DOM 0 layer here. That's our unique privileged guest. And that's working with the I/O, getting this information from the operating system and the input-output here, and passing it through the hypervisor, instead of the hypervisor doing its thing and operating as the conductor and doing its job there. So in this model here, it's very similar to the VMware model, but it has an additional layer on top of that situation. So let's talk briefly about data deduplication. And so we looked at one instance of data deduplication last time. Where we talked about different files being utilized in different places. Data deduplication is just it's a strategy for efficient storage. When we're talking about, it's similar to like the page sharing that we talked about. So let me try to give you a bit of a example here that might help make things a bit clearer. So if you imagine like an email server in a corporation, right? The vice president of human resources sends a 12-page document, and that's probably a little light for what a vice president of human resources would be sending somebody, but sends a 12-page document outlining changes in corporate policies to all the employees that work for this corporation. And all of the employees, knowing that this document is important, save this 2 megabyte document. So let's also say, this is, so now this 2 megabyte document is taking up 10 gigabytes of corporate disk space among all of these different corporate computers, just to throw out kind of an arbitrary number. It's a big company. It's taken out up 10 gigabytes. So 10 gigabytes might not seem like that much, but if you combine that one example with thousands of documents that are sent out and stored every day over years, that 10 gigabytes becomes 20 gigabytes, becomes 50 gigabytes, becomes 100 gigabytes, becomes terabytes, becomes petabytes, so on and so forth, right? So with deduplication, what we're doing is we're locating identical chunks of data in the storage system, flagging the original file, and then replacing the duplicates with pointers back to the original. So it's kind of like making a symlink on your desktop. You know, when you take and you're pointing, like you create a shortcut on your desktop to another file, or you create a link to another file. You know, that's essentially what we're doing here with data deduplication. You know, these chunks of data can be, you know, from anything really, from full files all the way down to small bite-sized data strings, right? So in each case, only one copy of the actual file or only one copy of the data is stored. So back to our example of the company with their email and all their space that was taking up. Instead of 10 gigabytes at that point, you know, the storage space gets compressed to around gets compressed to that original 2 megabytes, plus all the pointers from all the different machines going back to that original file. So what we have in our graphic here is sort of a before and after sort of illustration of how data deduplication works. You know, you can kind of see that it's happening at the byte level, the block level, and the file level. And when we work with data deduplication, we can reclaim between 30 and 90% of storage space on our network. You know, with all of our virtual machines on our network. So, you know, when you think about that in relation to somewhere like here at Cleveland Community College, and you think about all the zero clients we have on campus and all the labs that we have zero client devices in, you know, all those zero clients are pointed toward virtual machines. And all those virtual machines can share their data files thanks to data deduplication. Thin provisioning. So thin provisioning, as we mentioned, does not pre-allocate disk space when the file system is created, like thick provisioning does. So when you use thick provisioning, you're going ahead and you're pre-allocating all of the disk space that you're going to want to have for the entire system. But when you thin provision, you are allocating basically the max disk size. And it's going to put on there what it needs and then add more up to the max as you store more data onto the virtual machine. So, you know, it could lead to issues if the file systems actually fill the allocated space. So if you actually take and you fill up the entire space on a thin provision VM, you know, it could cause some problems. Mostly because each file system believes that, you know, it has more space available than it actually does. So if it consumes all of the allocated space, then you'll see some big issues that'll kind of compound on themselves. But if you have a good understanding of what you're going to need for your storage usage before implementing your virtual machine, thin provisioning can be an excellent tool to kind of economize your storage space so you don't waste things. When we get into the vSphere stuff, I recommend utilizing thin provisioning. We actually have to thick provision the server that ESXi goes onto, but then we thin provision the VMs that go onto the ESXi server. So when we get into vSphere, which we're doing now, you'll start to see all that kind of stuff. And if you remember back to memory overcommit that we talked about last week, and how, basically it could share the memory of different virtual machines, as long as one virtual machine wasn't using all of the memory, we could say, okay, we can allocate more memory than we have to, like if we have 10 gigabytes of RAM, we can allocate 8 gigabytes of RAM to all of our virtual machines, as long as the combination of the virtual machines aren't using the 10 gigabytes of RAM at once. So as long as they were kind of taking their turns and using 8 gigabytes at a time, or using like 6 and 1 and 1, or 4 and 2 and 2, or whatever, we could commit more memory to our virtual machines than we actually have on our host. And then the graphic we have here just kind of illustrates the idea of thick provisioning versus thin provisioning. Storage I/O control allows a quality of service policy assigned to a single VM or a group of VMs. So a quality of service policy gives certain traffic types greater bandwidth when contention is detected. So we talked about contention before in the past. From a hypervisor standpoint, VMware's hypervisor especially has the ability to assign storage priority on a VM by VM basis. So we're guaranteeing appropriate resources for applications that have been designated with more important resource-constrained situations. So as we kind of see here, if we have a policy in place where we have a really important VM that needs to be getting data. In the first half of our graphic here, we have a really important VM that needs to be getting data, but it's constrained on bandwidth, and the secondary VM is kind of getting all the I/O storage bandwidth. That's the thick line and the thin line there. So this graphic's kind of strange because it's they're supposed to represent the same VMs on both sides of the graphic. So the first VM, which is designated as the important VM, is also the first VM, the important VM on the second side. Just the colors are, I can see how they can kind of be confusing, but the idea being that, with the quality of service policy assigned here, it's maintaining that we need to switch this over to where this important VM gets the bandwidth that it needs. So we're guaranteeing appropriate storage throughput for this important VM, for these business critical applications, versus the other VM that, might not be as critical, might not have as important of things on it. Just some other things here. This is the last slide, so we'll let it go here. We just have some other topics to kind of round us off here. Tiered storage, which are storage arrays that have different classes of storage, offering multiple levels of service. Essentially what we're doing there is we're using different types of storage with varying performance and availability properties to service an application's requirements. So an application that requires top-notch performance and availability would be deployed on faster storage, maybe with some kind of RAID capability. And an application with less stringent demands might be placed on some slower disks with little or no availability options. And we can put all of these storage types on the same data storage array. And then the data that comprises these particular applications can be migrated from one tier of storage to another tier of storage as the application requirements change. So we can dynamically migrate those files based on need. That's depending on the vendor solution. This can be done dynamically. Or you can also go backwards. You can demote them back through the ranks if you determine that you don't need it as much. Solid state drives use solid state memory instead of spinning platters. 50 times faster than current disks. So, we just put solid state drives in there. You should all know about solid state drives by now, and knowing about the benefits of solid state drives. We've kind of mentioned the importance of speed and I/O speed in terms of how fast our server applications run. Hey, Jonathan, just saw your question there. Allowing virtual machines to share data through data duplication, might that become a security risk? Well, insofar as the way data duplication works, understand, is that the data is on both machines. So instead of so it's recognizing, it's basically doing file comparison and seeing that we have the same file here. So instead of having this file, we'll just point a link from this file to this original file. So the data has to be on both machines. So there's not an open share to the world insofar as it's not open and out there. Both people have to have the file. And then I would assume that if that original file were somehow manipulated, and that's something that I don't know much about, I would assume if that original file got manipulated and changed its signature somehow, then it would change the link and it wouldn't be available anymore. So it would go back to the previous downloaded version maybe, That's something I actually don't know a ton of stuff about. So I might have to look into that part and maybe get back to you on that. But in terms of just like information security, since both hosts have to have the file somehow, you know, they would have already had it. So I would say that it's not a big information security risk, but could pose some sort of data risk depending on how it handles manipulated data. If that makes sense. But with, back to our slide, with SSDs, we talked about the importance of speed and how speed makes a huge difference with our virtual machines in terms of the read-write speed. So an SSD can significantly decrease the deployment time of a virtual machine. It could also drastically improve the performance of the virtual machine. So it's something to consider, as we talked about last week when we were talking about building out our ideal deployment environment, our ideal deployment server for virtual machines. And we talked about, like, if you're going to over-engineer anything, throw a bunch of RAM into it, throw a bunch of memory into it. And if you're able to, throw some solid state drives in there. It's a little more costly, but it'll help you out in the long run. So make that deployment a lot faster, make those virtual machines a lot faster, run those applications a lot faster. I'm going to skip that last point there about storage virtualization. It's not a big deal, and we've kind of flown past our time here. So I'm going to leave it there, and that's going to be all for today. Thank you all for joining me. Had some good questions today. Interesting stuff about virtualized storage. I'm going to hang out in the chat for just a minute, turn back on the music, and answer some questions in the chat for just a moment. But that's all that I have for today. Thank you all for joining me, and we'll see you next time. This policy is multiple levels of service.